And many power companies keep records of past events in the form of trouble tickets. Whenever something is happening, a problem is happening, even a flicker of light, and the customer is just complained about that, it calls the dispatchers, and we have all the phone calls, they have the trouble tickets about everything that you call the utility companies. Either very serious event, like the fire that I showed you, or even the flickering of lights. So they have thousands of trouble tickets like this. And they have inspection reports. Whenever an inspection maintenance crew went inside the manhole, they are filling the reports, inspection reports. And they know all the cables. They have all the cable information, all the equipment switch transformer information, the materials, when are they installed. They have all this information about the manhole. So we thought that we can use all this data to characterize those electric structures. So now each electric structure has some features, attributes, and with lots of data. So and we can find some patterns. We can find some interesting patterns in this data. And then we use machine learning to make predictions. We now know the past data and what kind of electric structures had problems before. And we can just analyze this data, we can characterize it, and we can create a model, and then we use this model to predict the future electric structures which can create problems. So we use machine learning for ranking of the electric structures according to their vulnerability to the explosions. So machine learning is a branch of artificial intelligence, and it's the design and development of algorithms that allow computers automatically learn to recognize complex patterns and make intelligent decisions based on data. Actually, all of us are familiar with machine learning algorithms. When in the 90s, Kasparov was playing chess with the computer, actually it was playing chess with a machine learning algorithm background. And when last year, when the Watson won the Jeopardy challenge, again, it was machine learning. And whenever you see a robot, it's most probably running a machine learning algorithm. So what I do is I design machine learning algorithms. I do mathematical modeling in order to rank the electric structures. So thank you.
Yeah, this talk is going to be on the use of electroelastic systems for energy harvesting, and we're going to be talking about power levels, orders of magnitude less than my colleagues mentioned. So low power generation using electroelastic dynamical systems is going to be our discussion. And just a very, very brief background about myself within the last decade. I got my, I don't know if this is going to stay or not. I got my bachelor's and master's degrees back from Turkey, Middlesex University in mechanical engineering, 2004-2006. I did my work with Nevzat Özgür, and I guess I understand he's president, my vice president of Middlesex University. I was very much interested in the theory of structural dynamics and vibrations, which made me decide on my PhD more subject-oriented. And this school, the Engineering Science and Mechanics program at Virginia Tech, had hosted jams for decades on the field of structural dynamics, vibrations, and dynamical system theory. So this is where I went for my PhD and got my PhD in engineering mechanics in 2009. And I was fortunate to interview a week after my defense at Georgia Tech. This is back in 2009 again. Got the offer, accepted, but I had to wait for 1.5 years for the budget situation of the state of Georgia to be cleared. And since last summer, I've been working at Georgia Tech as an assistant professor of mechanical engineering. And so I have a brand new research group over there. And my group works on problems of smart materials and structures and their dynamics, and these days very much focused on energy harvesting. This is what is connected to this panel's discussion. So we're going to be talking about low power generation from mechanical energy, the waste mechanical energy. And the main motivation in this research field is due to the reduced power requirements of small electronic components, such as this is a schematic over here I found on the internet. It's like a sensor network system that is being used in various types of civil infrastructure systems, just like a bridge. Let's say you have a suspension bridge. On such a bridge, you have hundreds of such sensors acting and communicating with each other, and usually there's some data transmission, and the level of power consumption is on the order of microwatts to milliwatts. And it is therefore possible that the research goal or the question is, would it ever be possible to use the ambient vibrations, let's say, or low power wind or low speed wind to power these devices and to make these wireless sensors entirely self-powered and autonomous? So there are many ways you can do that. Using piezoelectric materials is one powerful alternative for a number of reasons. First of all, piezoelectric materials do offer very high power density as compared to other transduction mechanisms like electromagnetic induction or electrostatic transduction. This graph over here is from a review article on the subject of energy harvesting. This shows power density, this power output per device volume versus the voltage output. This pinkish portion over here is the largest area belongs to piezoelectric materials. And well, obviously, solar cells are over here, orders of magnitude larger power. It's not we're discussing really low power generation here for small electronic components. And what you see over here is there's a significant overlap in the power density level of piezoelectric materials and lithium ion-based technologies, just like what you use in your cell phones and batteries. So can we harvest the energy and and enable some self-power systems so that there is no need for battery replacement? It is extremely expensive. Maintenance costs for such wireless sensor network systems is extremely expensive. And the chemical waste of batteries is also a present issue. So piezoelectric materials turn out to be very, very attractive. You can get pretty large voltage levels directly from the material itself with its constitutive behavior. And you don't need to put a bias voltage, unlike the case in electrostatic transduction. And the MEMS scale and mesoscale fabrication techniques are quite mature. So I mentioned the mechanical energy source, what type of sources that we might have. We might have ambient vibrations, for instance, in a bridge like this. This is a 3-span, pretty short bridge in Roanoke, Virginia. This data was taken during a RISC project in 2009. Typical strain fluctuations at an arbitrary point on the bridge due to, let's say, traffic and the wind loss, of course. And you might also measure, let's say, the acceleration. So you can think of putting some piezoelectric patch to convert structural vibrations into electricity. That's a type of material. This property is that. Unfortunately, we don't have enough time to cover the kind of details about smart materials. Or you can put a little cantilever with piezo layers, and the base acceleration can be used as an input to generate electricity. There are many other sources in such civil infrastructure systems, like flow energy, which could be airflow. Could even be due to, let's say, you may have some vehicles passing through some block body that you locate. You can create some vortex street behind the block body, or it might be completely turbulent, or like if you have a smooth block body, it won't come on vortex street. And you can locate your piezo at the back and create vibrations on it to generate some low power electricity. And people already use in such turbofan kind of engines and in these similar noise sources, acoustic liners, certain metamaterials. These things absorb noise, and the question is then, in fact, we just put together an NSF proposal on this thing. Why don't we just take that noise and generate electricity out of that noise? So you can imagine, therefore, sound waves or structure-borne waves also a source of energy to, let's say, power the aircraft sensors. And here's how this intersects with the discipline of dynamical systems theory, if you like. That's my passion. Here's one way of harvesting energy or creating energy by using, let's say, base acceleration. This end of the cantilever over here is a fixed free beam with piezo layers and some elastic layer. Typically, we use a tip mass over here to design this guy. It's located on, let's say, on the bridge, and you know what your input is, typically the frequency content. You can design this guy to match the fundamental resonance frequency with the excitation frequency for the maximum performance. This kind of design is called a linear or a resonant energy harvester. And the main challenge in these things is that, here we go. Anyone? The main challenge in such linear design is that these are very lightly damped, if you like, high quality factor configurations. So the optimal performance is very limited within a narrow bandwidth of operation, and that's been it's fine. I'm good. All right. That's what made us and some other groups interested in nonlinear dynamic configurations. If you have a similar cantilever of this sort, suppose that this is made of a ferromagnetic material, and I put two magnets over here, it becomes a bistable system with such a simple modification. And bistable systems can exhibit all sort of nonlinear dynamic phenomena, such as chaotic response. If you have any background, this would be the Poincaré map of the chaotic response, this fractal-shaped evolution of the dynamics. Harmonic input, so you can imagine this shaker as your, let's say, bridge or something like this, a mesoscale just for prototype purposes. And piezo patches are over here. And to give you an idea why nonlinear dynamic systems are so interesting, it's the exact same frequency and slightly increased excitation amplitude. The response form turns into what we call high energy limit cycle oscillation. So transient chaos turns into high LCO. And the nice thing about such a design is that this kind of nonlinear dynamic phenomena takes place over a range of frequencies, unlike linear resonant configurations. What my group does at Georgia Tech at the present is also some multifunctional problems of energy harvesting. My PhD was funded by Air Force R. So Air Force had interest in obviously using these things for unmanned air vehicles. But at the present, I'm more interested in underwater applications. This, for instance, also uses piezoelectric materials. So fiber-based piezo laminates are over here. It's basically, you can tell that this is trying to mimic fish-like locomotion, but it's fixed obviously in still water. It's the first vibration mode. This will be the second vibration mode. So you can basically operate in the piezoelectricity is a reversible thing. So you can put the voltage input and create vibrational output. So then the question becomes, why don't we all use this guy as a power generator for underwater applications, and let's say harvest some energy and store some, structural battery to reuse it for locomotion for a Navy mission, let's say. So this is a typical case. I found PhD students looking into this modeling of these things, also free locomotion. Just a few more examples to conclude. Another way, for instance, of generating low-power electricity, you have flow coming from here, and this is a collaboration with the University of São Paulo in Brazil. To basically introduce piezoelectric coupling to aeroelastic designs, which are scalable to work as wind generators. And John had a talk on photonic crystal systems. This would be a phononic or metamaterial system where we try, this is a collaboration with the Aerospace Department at Georgia Tech. We try to localize the wave input over here at a specific point so that we can get the entire energy on the harvester itself, and you can create some imperfections again to localize the energy for optimal energy harvesting. Just one last example is like the next generation energy harvesting concept that we again proposed to NSF with a collaborator at the University of Houston. He does atomistic simulations, and he had shown in a couple of PRL papers that there's something called, basically, there's already known that any elastic dielectric can show charge separation, but that becomes important only at nanoscale. So basically, we are trying to go down to come up with cantilevers of a few nanometer size and to make some generators out of them. So the bottom line is these are microwatts or milliwatt power generators, but it becomes important at large scale because it might be possible to avoid maintenance kind of costs at large. Thank you very much.
John.
Yes. Yes.
But I'm also curious about.
Can you please talk with a louder voice?
Sure. So I'm still curious about what are the bottlenecks that prevents increasing gallium nitride LED efficiency, especially that relates to material quality, dislocation density, for instance.
Sure. Well, the main bottleneck with trinitride technology, gallium nitride based technology, is the substrate. So in order to grow these compound semiconductors, you need a wafer host substrate on which you can deposit this material. And typically, this, of course, as you are going to do this in large scale, to compensate for the lightning technology, you need this substrate to be widely available as well as affordable. And the common substrate that's used is the sapphire, which has around 13 to 16% lattice mismatch. So what it means that for every 13 chairs, you are missing one chair, and that lane will eventually affect the other people because they cannot sit. So you cannot arrange the atoms fully crystallographically. So that's the main problem with trinitride. But specifically, silicon carbide is the problem with silicon carbide is it's very expensive. It's like around 100 times more expensive than sapphire. So that's one of the bottlenecks. And there are only one company that works on silicon carbide right now, but they have considerable efficiency. And in terms of LEDs, the general, for specifically LEDs, the biggest problem right now is what's called droop, which means that to achieve high power, you need to inject more carriers, more electrons, and the more you inject, although you get more light out of it, the overall efficiency tends to drop. So you get less photon per electron as you inject more. So that's one of the bottlenecks, and that has to do that has to do with the optimization of the growth as well as the structure, because of the like piezoelectric fields that is inherent to this material system.
The solar energy storage and conversion. Have you looked at a large-scale commercial production? I'm just trying to get an idea what it might look like.
Those are very good questions. So we all do our experiments in the lab scale, and of course we are discussing about how can it be available to very large scales. But it's so because we are trying to convert solar energy to the fuels. So that's here comes the practical part, because the whole world is already the infrastructure. There is infrastructure for fuels. So if we can separate, if we can produce the fuel on site, where, for instance, on large flat sites, like on the sea, for instance, using the water from the sea, the salty water and sun, and using the CO2 from the atmosphere, and directly producing the fuel, and through the pipelines that is already available, distribute the fuel and energize. So, and the second question.
How many years do you predict that will be?
It's very hard to make predictions about the future because unfortunately governments about this renewable energy generally research is it becomes much faster when there is an oil crisis. When the oil is cheaper, people usually don't care about renewable energy, unfortunately. But it really depends on the oil prices, I think. If we have an oil crisis in the future, again, the research on this will increase, and people will be much more aware of the fact that we don't have a renewable energy from the fossil fuels. Maybe 50 years, maybe 100 years.
Yes, please.
Follow up for that question, Anil. Do you think this can be coupled with carbon capture and storage, or carbon capture and separation, and can be peak for your technology?
Exactly. So carbon capture, this is one of the viable option. So one of the prominent scientists actually they suggest to people, if you want to make money for the future, just buy the already consumed oil wells, because in the future they can be rented to the companies, so they can push CO2 and capture and store there for the future fuel generations. So it's very much related to the CO2 capture.
Okay. Yes, please.
My question is to Dr. Ertekin, not Dr. Erturk.
Okay.
You have an emphasis on trouble tickets as the data that you're processing.
Yes.
How much sensor data is available?
How much sensor data?
How much sensor data is available?
Not much.
Or are you using any of it? Or are there, for instance, any feasibility studies as to, if we had sensor data here, there, would it simplify things, or how expensive would it be, that kind of thing?
Currently, as I said, the grid is old, and in the smart grid initiatives, this is one of the aims. Put sensors to everywhere so that we can gather data from that, and we can use this data to make it smarter. But since the grid is, very huge, we cannot put all these sensors overnight there. And right now, the numbers of the sensors are very limited. Because it's not a priority right now. The priority is right now just to make the grid reliable with the current information, and then this other extra new devices and the smartness from the new devices and new equipments will come later on.
But the intelligence of your work is probably, or what your work does is probably to compensate for lack the sensors to actually compensate for it from the trouble tickets, right?
To compensate the data which will come from sensors.
Information from
Yeah, we can in some sense we can say maybe compensate, but in some sense we can get some information that we cannot get from the sensors in the very near future, because I mean we have lots of data, lots of information about the electric structures, but to make them all sensor-wise will take a lot of time, and we cannot wait and sit till all the places are full of sensors. We need to do something right now. We need to do something till it gets smarter.